All right, we're in section 2.4, using derivatives to find absolute maximum and minimum values. Um, Really, if you followed how to do local max and min values and some of our ideas behind derivatives, this will probably be one of the easier sections that we do. And the video for this should actually be relatively short. I think the concept is really simple. The objective here is to simply find absolute extrema. Again, extrema meaning maxes and mins. Vocabulary, absolute max, absolute min, and the extreme value theorem. Okay, it's not a theorem that you're going to have to necessarily know by name so that you can say, oh, I use this theorem to do this. You just have to understand what it's saying in order to be able to use it. Okay, so absolute value, absolute maximum, absolute minimum. It is exactly what it says. Absolute meaning the greatest or the only, the highest and lowest values. Absolute maximum, absolute minimum, the highest and the lowest y values on the graph. So if we look at the graph on the right, on the interval from A to B, so from A, from right, whoops, from A to B, so the first endpoint to the last endpoint, you have minimums at C1. There's a local minimum right there. You have a minimum at C4, another local minimum right there. And you have a relative maximum at C3. However, on the interval from A to B, the relative minimum at C4 happens to also be the absolute minimum value. It is the lowest possible place on the graph. The one at C1 is just a relative minimum. It's not the lowest possible place on the graph. This one right here is. Now I also have a relative maximum right here at C3. It, however, is not the highest point on the graph. The highest point on the graph actually occurs at the endpoint over here at B. Okay? So hopefully, again, you guys can understand that the relatives that we might find, the relative maximums and minimums that we might find, could possibly be the lowest points on the graph, but then there's also the possibility that they are not, and that one of the other places that we have to check are going to be the endpoints, because that's where you could have an absolute max or an absolute minimum. So the definition, it's really very straightforward. F of C is an absolute minimum if f of c is less than or equal to all the other f of x values. Basically, if it's the lowest y value on the graph. And then f of c is an absolute maximum if f of c is greater than or equal to all the other f of x values on the graph. The extreme value theorem, and again, you don't have to necessarily know this by name, but it should make sense. If f is continuous on a closed interval, our function that we looked at up here was continuous, and it's continuous on a closed interval because the endpoints a and b are included in the graph, then f must have both an absolute maximum value and an absolute minimum value on the interval from a to b. You have to have a highest and a lowest value on a continuous and closed interval. Okay, it has to happen. There's just no other way to do it. So as we saw in the picture above, the extreme values can occur at either a relative extreme or at the boundaries. So there's a lot I'm saying right here, which is really just kind of going through the actual mathematics of it. Really, the easiest thing to do is to find these. This is not going to be difficult. You are simply going to find your relative extrema by doing the first derivative test. You're going to take the first derivative, you're going to find your critical values because that's where you can have relative max and mins. And then all you're going to do is you're going to take those values and the endpoints, because the endpoints could be included, and test all of those values in the original function. Whatever the biggest value is that you find and whatever the smallest value is that you find are your absolute max and min values. Let's go ahead and do an example. So our first example, Find the absolute maximum and minimum of f of x equals x cubed minus 3x plus 2 on the interval from -2 to 3/2. So the fact that this is a continuous function and the fact that this is a closed interval, and I know it's closed because it's got the solid brackets or the squared off brackets, means that there will be an absolute maximum, absolute minimum on this graph. So let's find out what that would be. First thing we're going to do is we are going to take the derivative. So we'll take the derivative and we're going to get 3x squared minus 3. To find the critical values, we set that equal to 0. Let's see, we can divide a 3 out, so we get x squared minus 1 equals 0, meaning that my critical values are at x equals plus and minus 1. Now, I don't have to create a little number chart here or anything, because all I'm going to do is I'm going to take those two values, and for me, this is the easiest way to do it. I'm going to create a little chart. This is going to be my x value. This is going to be my f of x or y value. I'm going to have to test 1 and -1. I'm going to write them in order, -1 and 1. Those could be my absolute max and absolute min values, but I also have to test the endpoints. So I also need to test -2 and 3/2. Okay, 3/2 will take a little extra work to be able to figure out. The other ones we should be able to do pretty easily just by talking through it. If we take -2 and we plug it into the function, we're going to get -2 cubed. That's -8. And then -3 times -2 is +6. So -8 plus 6 is -2 plus 2 more is 0. If I take -1 and plug it back into f of x, -1 cubed is -1. -3 times -1 is +3. So I get -1 plus 3 is 2, plus 2 more is 4. If I take +1 and plug it in, I get 1 minus 3, which is -2, plus 2 is 0. And then 3/2, again, 3/2 is going to take a little bit of extra work. You might want to use your calculator for this one, and that's okay if you need to. If you plug 3/2 back in, you're going to get 7/8 as a fraction. Whoops, 7/8, which is equivalent to 0.875 in this case. So all you need to do now is you need to look at the values that we just got. What's the highest value? What's the lowest value? Well, the biggest value that I got was 4. The lowest value, I actually got it twice, is 0. It only needs to be done once. So all we need to say now is that the absolute maximum is f of -1 equals 4. And the absolute minimum, and I could use either one of these. You could say f of -2, or you could say that that's equal to f of 1, and both of those equal 0. So the absolute maximum is 4, absolute minimum is 0. Okay? All right, second example, find the absolute max and absolute minimum of the function 8 natural log of x minus x squared on the interval from 1 to 4. Now you do have to double check because this has a natural log in it. It's not just a polynomial. Remember, the domain of natural logs is anything greater than 0. And the fact that we started at 1 here in our closed interval means that this is a continuous function on a closed interval. We have to have a max and a min absolutes in this case. So let's go ahead and take our derivative. So we'll get f prime of x. The derivative of 8 natural log of x is 8 times the derivative of the natural log of x, which is 1 over x, minus 2x. Need to find our critical value, so we'll set it equal to 0 or figure out where it's undefined. So what I'm going to do here is I want to get rid of that x out of the denominator. So I'm going to add the 2x to both sides. So 8 times 1 over x is 8 over x. And I'm going to add the 2x to both sides. And I want to get that x out of the denominator. So I'm going to multiply both sides of this thing by x. So that's going to give us 8 equals 2x squared. Dividing both sides by 2, we get that 4 equals x squared. And therefore, x equals plus or minus 2. There's our critical values. Now all we have to do is set up our chart. Okay, I know I'm going to have x here. I'm going to have f of x here. I know I have to test my endpoints of 1 and 4. And according to this, x equals plus or minus 2. I don't need to check the negative 2 because that's not even in my domain. Up here, we didn't even start with a domain that went to negative 2. We couldn't have because the x values have to be greater than 0. So I only need to check 2. So let's go ahead and plug these things in. So if I plug 1 in, I'm going to get 8 times the natural log of 1, but the natural log of 1 is 0. Minus 1 squared, so that's going to give us negative 1. Not too difficult there. The next two are going to be a little bit more challenging. I'm going to get 8 times the natural log of 2. 8 times the natural log of 2 minus 2 squared, which is 4. And then the last one, I'm going to get 8 times the natural log of 4 minus 4 squared, which is 16. We're probably going to need to plug those into a calculator so we get some kind of a decimal approximation here so that we can actually see which one of these things is going to be a bigger or smaller number. So I'm going to go ahead and plug these in. And it's probably a good thing I did. The 8 natural log of 2 minus 4 is approximately 1.55. And the 8 natural log of 4 minus 16 is approximately negative 4.91. Okay, and I definitely needed that value because, as it turns out, that is the smallest value. So this one is my min, and my max comes from that one right there. So we've got an absolute maximum, which is f of 2. And I'm going to write the actual exact answer, not the decimal. 8 natural log of 2 minus 4. The absolute minimum is f of 4. And again, I'm going to write the exact answer, not the decimal, which is 8 ln of 4 minus 16. And there's your absolute max and absolute min. All right, one more example. So what if we're not given a closed interval? Well, if we're not given a closed interval, we can't use the extreme value theorem, but we might still be able to find extreme values. So just know that the theorem here doesn't actually apply, but we might still be able to actually find extreme values. So what you have to do is you have to know something about the domain here, and then be able to see what you know about this graph and what you know about its domain to figure this out. So we want to find the absolute maximum and minimum values, if they exist, for g of x equals x squared natural log of x on its domain. Well, the domain of that, you can plug anything you want to into x squared, but I can't plug anything I want to into natural log of x. So the domain for this is that x must be greater than 0, or from 0 to infinity, again, not including 0, but that's because of the natural log part. So we at least now know what our domain is. So we still want to take a derivative. Let's go ahead and take a derivative, g prime of x. And let's see, that's going to end up being a product rule. So that's going to be the derivative of the first one, which is 2x, times the second one, natural log of x, plus the derivative of the second one, which is 1 over x, times the first one, which is x squared. Okay, I'm going to want to set that equal to 0 to find my critical values. Remember, I don't have endpoints here because this thing goes from 0 to infinity, but you can't include either 0 or infinity. As a matter of fact, let's write the domain as 0 to infinity. So we can clearly see there's no endpoints for me to check here. So really the only things that we can check are critical values. So let's go ahead and continue to find our critical values. So let's see, we're going to have 2x natural log of x plus simplifying 1 over x times x squared is just x. Set that equal to 0. In order to solve this, I can actually factor out an x, which is going to leave us with 2 natural log of x plus 1 equals 0. Okay, so that means that either x has to equal 0 or 2 natural log of x plus 1 equals 0. Well, x equals 0 is done. We need to solve the other one for x, so we're going to have to subtract 1 on both sides. We're going to have to divide by 2. So it's wherever the natural log of x equals 1/2. Well, solving that one is going to be a little bit more difficult. We need to actually change this into an exponential. Remember, we don't typically write the base here of e, but just remember that there is a base of an e there, and e raised to this is going to give me the x. So ultimately, x here is going to be e to the negative 1/2 power. So what we need to do now is we need to plug those back in. We're still going to create a chart. We're going to call this x. This is f of x. We're going to plug in 0, and we're going to plug in e to the negative 1/2 power. Let me write that negative 1/2 again. Okay, so if we plug 0 into our function, well, we can't. It's out of the domain. So that shouldn't have even been a possibility. Doesn't work. It's not in the domain. So now all we have to do is figure out, okay, what does this graph look like? Is this e to the negative 1/2 going to be a maximum or a minimum? Well, hopefully what you know of x squared ln of x tells you that this is going to be an increasing function constantly. So this really should be a minimum value. So let's go ahead and check that out. As a matter of fact, if we were to plug in e to the negative 1/2, let's just see what we're going to get. That's going to be e to the negative 1/2 squared times the natural log of e to the negative 1/2. Well, e to the negative 1/2 squared is just going to be e to the negative 1. Natural log of e to the negative 1/2 is negative 1/2. So what we really get here is negative 1 over 2e, simplifying. Okay, change the e to the negative 1 to 1 over e and then multiply them. So you get negative 1 over 2e. So let's go ahead and just see if what I said was correct. We're going to put on our number line e to the negative 1/2 power. If I test something which is just less than e to the negative 1/2 power, so e to the negative 1/2 power is 1 over the square root of e. That's what that value is. So if I'm going to take something and divide by that, well, I'm going to have to put in some really small numbers. It's probably going to be easier actually to pick a bigger number than that. So something bigger than e to the negative 1/2 power would just be e. So if I take e and I plug it in, I'm going to get e squared times the natural log of e, which is 1. So that's going to give me e squared, which is going to be a positive value. So I know that the function would be, oh, I'm sorry, I plugged that back into the original. Got to plug it into my derivative. I apologize. So if we plug that into the derivative, which is x times 2 natural log of x. So if I take e and I plug it in, I'm going to get e times 2 times 1 plus 1, so 3e. That's still positive. So I was right the first time. That's going to be increasing. Now the question is, what happens if I put something in which is less than e to the negative 1/2? And just so you don't think that I actually knew this off the top of my head, e to the negative 1/2 is approximately 0.61 or so. I actually had to plug that one into the calculator to figure that one out myself. So something less than 0.6, I can't use 0, can't use negative numbers, but I could use 0.5. So if I plug a 0.5 back in, once again, I'm plugging it in here. Whoops, plugging in here. 0.5 on the outside gives me a positive, so it's really what happens on the inside of that parentheses. Well, if I take the natural log of 0.5, natural log of anything in between 0 and 1 is going to be a negative value. The question is, well, is it going to make the inside a positive or negative? So if I do 2 times the natural log of 0.5 and then I add 1 to it, I get a negative value on the inside of this parentheses right here, which means I get a negative times a positive, which means that this is negative, was decreasing there. What we indeed had was a minimum. Now, I went through a lot of process there to figure that out, but that is probably the easiest way to do it, by using your calculator for values that aren't just quite so easy to figure out without knowing, like, if it's just 1 or 5 or something easy like that. So really what we have here is an absolute minimum. There are no absolute maximums in this case. So we have an absolute minimum, which is f of e to the negative 1/2 power, which works out to be negative 1 over 2e. And that's it.